Welcome to today's problem walkthrough. In this session, we will explore problem number 1748, sum of unique elements. This problem challenges us to think critically about iterating through arrays and efficiently identifying unique elements. Let's dive in and solve it together. In this problem, you are given an integer array called nums. Your objective is to calculate the sum of all the unique elements in this array. Now, what do we mean by unique? An element is considered unique if it appears exactly once in the array. For example, if a number shows up more than once, it's not unique, and we won't include it in the final sum. Let's also clarify the input and output formats. The input will be an integer array nums with a size between 1 and 100. The size of the array is denoted by n, and it will always have at least one element. The output will be a single integer, which represents the result of summing all the unique elements in the input array. To make this concept clearer, let's go through a few examples. In the first example, the input array is nums equals 1, 2, 3, 2. Here, the number 1 appears exactly once, so it's considered unique. Similarly, the number 3 also appears exactly once, making it unique as well. However, the number 2 appears twice, so it is not unique. When we sum the unique elements, we get 1 plus 3 equals 4, which is the output. In the second example, the input is nums equals 1, 1, 1, 1, 1. All elements in this array appear more than once, meaning there are no unique elements at all. The sum of unique elements is therefore 0. Finally, in the third example, the input is nums equals 1, 2, 3, 4, 5. Here, all the elements are unique because each number appears exactly once. The sum of all unique elements becomes 1 plus 2 plus 3 plus 4 plus 5 equals 15, and that is our output. Now, let's look at the constraints and edge cases we need to consider. The array size will always be between 1 and 100, and each element in the array will have a value between 1 and 100. There are several important edge cases to keep in mind. First, if all elements in the array are unique, the sum will simply be the sum of all the array elements. On the other hand, if all elements are duplicates, meaning no unique elements exist, the output should be 0. For an array with just one element, that single value is the sum since it's inherently unique. We also need to ensure that our solution handles both small input sizes, like an array of size 1, and large input sizes, like an array of size 100, efficiently and correctly. These considerations will help us design a robust solution for this problem. To begin solving this problem, one intuitive approach is the brute force method, which focuses on counting and summing unique elements directly. The idea here is straightforward. For each element in the array, we count how many times it appears by iterating through the array again. If the element appears exactly once, we add it to our total sum. The steps are simple. Initialize a variable, total_sum, to 0, then for each element in the array, count its occurrences using a nested loop. When an element's count is 1, we include it in our sum, and finally, we return the resulting total. While this method is easy to understand and implement, it comes with a significant trade-off. The nested loops result in a time complexity of n squared, which makes it impractical for larger arrays. However, it does have the advantage of requiring no additional data structures, so its space complexity is 1. Ultimately, this simplicity comes at the expense of efficiency for larger datasets. Now, to address the inefficiency of the brute force method, we can turn to an optimized approach that uses a hash map for frequency counting. The motivation behind this method is to eliminate the need for repeatedly counting occurrences. Instead, we traverse the array once to build a frequency map, where each key represents an array element and its value represents how many times it appears. After constructing the map, we can simply iterate through it and sum the elements that have a frequency of 1. The steps involve creating an empty hash map, populating it with frequencies by iterating through the array, and then initializing total_sum to 0. Next, we loop through the hash map and add to the sum only those elements with a frequency of 1. This approach reduces the time complexity to n, as we only traverse the array in the hash map once each, and it uses n space to store the hash map. The trade-off here is that while we save significant time, we do use additional memory, which could be a consideration for environments with limited memory resources. Nonetheless, this method is far more efficient for larger arrays compared to the brute force approach. Another optimized alternative is to use Python's collections counter along with a set to simplify the process further. The intuition here is similar to the hash map approach, but by leveraging Python's built-in utilities, we can make the implementation more concise. The counter class automatically builds the frequency map for us, and we can filter it to include only the elements with a count of 1. Then, we directly sum up those filtered elements. The steps are straightforward. First, use counter to create the frequency map from the array. Next, apply a filter to isolate elements with a frequency of 1, and finally, sum these elements in a single step. This method maintains the same time complexity of O, n, because both the counter operation and summation are linear. It also has O, n, space complexity for storing the frequency map. The trade-off here is that while this approach is concise and improves code readability, it is functionally similar to the hash map approach. Additionally, relying on Python-specific utilities like counter may limit portability to other programming languages. However, it remains an excellent option for Python users. After evaluating the different methods, the chosen strategy is the hash map frequency counting approach. This solution strikes the right balance between efficiency and simplicity, achieving an optimal O, n, time complexity while being easy to implement. Although the counter-based alternative is concise and leverages Python's standard library, we select the hash map approach for its language-agnostic nature, making it applicable to a broader range of implementations. The brute force method, while simple, is dismissed due to its inefficiency for larger arrays. The key insight here is recognizing that counting frequencies efficiently with a hash map eliminates the need for nested loops, which simplifies the overall process significantly. Additionally, understanding that only elements with a frequency of 1 contribute to the sum allows us to focus our calculations. While the hash map approach does require additional space, the trade-off is justified given the significant improvement in time efficiency. With the problem constraints allowing for arrays of size up to 100, this method is optimal for both performance and ease of understanding. The problem asks us to calculate the sum of all integers in an array that appear exactly once. To start, we can use a brute force approach with nested loops. The intuition here is simple. For each element in the array, we count how many times it occurs using another loop. If the count equals 1, we add the element to a running total. The steps are as follows. First, we initialize a variable called total_sum to 0, which will keep track of the sum of unique elements. Then, we iterate over the array with an outer loop, where each iteration focuses on one element. For every element, we use an inner loop to compare it with all other elements in the array and count how many times it appears. If the count for that element is exactly 1, we add it to total_sum. After looping through all elements, the value of total_sum is returned as the result. While this approach is straightforward, its inefficiency lies in the nested loops, which result in a time complexity of O, n squared. This becomes problematic for larger input sizes. Let's walk through an example using the input array 4, 5, 4, 6, 7, 6. We start by initializing total_sum to 0. The outer loop begins with the first element, 4. Using the inner loop, we count how many times 4 appears in the array, and we find it occurs twice. Since it's not unique, we skip adding it to total_sum. Next, the outer loop moves to the second element, 5. The inner loop counts its occurrences and determines it appears only once, making it unique. So, we add 5 to total_sum, updating it to 5. For 6, the count is 2, so we skip it. Finally, we reach 7, which is unique, so we add it to total_sum, bringing the total to 12. At the end of the process, the result is 12, which represents the sum of all unique elements in the array. The brute force approach, while simple, is inefficient due to its O, n squared, time complexity. This makes it unsuitable for large input sizes, such as arrays with tens of thousands of elements. However, it can still be useful for small inputs where clarity and simplicity are more important than performance. To address the inefficiency, we can use an optimized approach that leverages a hash map to count frequencies. The intuition here is to process the array in a single pass, recording the occurrence of each element in a hash map. Once we have the frequency of every element, we can iterate through the hash map and sum up the elements that appear exactly once. This eliminates the need for nested loops, reducing the time complexity to O(n). The steps are as follows. First, initialize an empty hash map to store frequencies. As we iterate through the array, we update the count for each element in the hash map. After building the frequency map, we initialize total_sum to 0 and iterate through the hash map. For any element with a frequency of 1, we add it to total_sum. Finally, we return the total sum. Let's revisit the example input 4, 5, 4, 6, 7, 6 to see how the optimized approach works. First, we initialize an empty hash map. As we process the array, we populate the hash map with the frequency of each element. 4 appears twice, 5 appears once, 6 appears twice, and 7 appears once. The hash map now looks like this: 4, 2, 5, 1, 6, 2, 7, 1. Next, we initialize total_sum to 0. Iterating through the hash map, we check the frequency of each element. For 4, the frequency is 2, so we skip it. For 5, the frequency is 1, so we add it to total_sum, making the total 5. For 6, the frequency is 2, so we skip it. For 7, the frequency is 1, so we add it to total_sum, bringing the total to 12. At the end, the algorithm outputs 12 as the sum of unique elements. By utilizing a hash map, we achieve this result in linear time. Additionally, the hash map structure ensures that we only use space proportional to the number of unique elements, making it highly efficient. When comparing the two approaches, we can see clear differences in efficiency. The brute force solution has a time complexity of O(n) squared due to its nested loops, while the optimized solution reduces this to O(n) by using a hash map. The space complexity of the brute force method is O(1), as it doesn't require additional data structures, whereas the optimized approach requires O(k) space, where k is the number of unique elements stored in the hash map. Despite this trade-off, the optimized approach is far superior for larger arrays. Let's also consider edge cases. If the input array is empty, the algorithm should return 0 since there are no elements to sum. If all elements in the array are unique, the result will simply be the sum of all elements. If no elements are unique, the result will be 0, as no elements meet the criteria. Finally, for an array with a single element, the algorithm returns the element itself, as it is inherently unique. These considerations ensure the algorithm is robust and handles a wide range of scenarios effectively. The solution begins by defining a class solution and its method SumOfUnique. This method takes a list of integers, nums, as input. The goal is to calculate the sum of elements that appear exactly once in the list. First, we initialize an empty dictionary called frequency. This dictionary will store each number as a key and its corresponding count as the value. To populate this dictionary, we iterate through the list nums. For each number, if it already exists in the dictionary, we increment its count by 1. Otherwise, we add it to the dictionary with an initial count of 1. This step ensures we know how many times each number appears in the input list. Next, we initialize a variable unique_sum to 0. This variable will store the cumulative sum of all numbers that appear exactly once in the list. We then iterate over the items of the frequency dictionary. For each number and its count, if the count is exactly 1, we add that number to the unique_sum. Finally, the method returns the value of unique_sum, which represents the sum of all unique elements in the input list. This approach ensures that we efficiently compute the desired result in linear time relative to the size of the input list, making it optimal for this problem. This is the Java implementation of LeetCode problem number 1748, sum of unique elements. The solution uses a hash map to count the frequency of each number in the input array. The getOrDefault method is used to efficiently update counts. After populating the frequency map, we iterate through its entries to compute the sum of numbers that appear exactly once. This logic mirrors the Python implementation while adhering to Java's syntax and conventions. To solve the problem of summing up unique elements, we start by working with an example where the input array is nums equals 1, 2, 3, 2. The first step involves initializing a dictionary called frequency. This dictionary will help us keep track of how many times each number appears in the array. Initially, the dictionary is empty, as no numbers have been processed yet. Next, we iterate through the array and update the frequency dictionary. When we encounter the first number, 1, it gets added to frequency with a count of 1. Then, we see the second number, 2, and add it to the dictionary with a count of 1 as well. When we process the third number, 3, it is also added with a count of 1. At this stage, every number in the dictionary has a count of 1, meaning all numbers are unique so far. As we continue iterating, we encounter the fourth number, which is 2. Since 2 is already in the dictionary, we simply increment its count, making frequency equals 1, 1, 2, 2, 3, 1. With the frequency dictionary fully populated, we move on to the next step, calculating the sum of unique elements. To do this, we initialize a variable called unique_sum and set it to 0. Then, we iterate through each item in the frequency dictionary. The first number, 1, has a count of 1, which means it is unique, so we add 1 to unique_sum, giving us a running total of 1. The second number, 2, has a count of 2, meaning it is not unique, so we skip it. The third number, 3, has a count of 1, which makes it unique, so we add 3 to unique_sum, resulting in a final value of 4. Therefore, the sum of unique elements is 4, and this is the value we return. Now, let's look at another example where the input array is nums equals 4, 4, 4, 4. As before, we start by initializing the frequency dictionary, which is empty at the beginning. Then, we iterate through the array to populate this dictionary. The first occurrence of 4 is added to frequency with a count of 1. For each subsequent occurrence of 4, we increment its count, so by the end of this step, frequency equals 4, 4. Next, we calculate the sum of unique elements. We initialize unique_sum to 0 and examine the entries in the frequency dictionary. The number 4 has a count of 4, which means it is not unique, so we do not add it to unique_sum. Since there are no other numbers in the dictionary, unique_sum remains 0. Thus, the sum of unique elements in this case is 0, and we return 0 as the output. In the third example, the input array is nums equals 5, 7, 5, 9, 10. We begin by initializing the frequency dictionary, starting with it empty. As we iterate through the array, we process each number to build the frequency dictionary. The first number, 5, is added to the dictionary with a count of 1. When we encounter 5 again, we increment its count, resulting in frequency equals 5, 2. Next, we see the number 7, which is added with a count of 1, giving us frequency equals 5, 2, 7, 1. Then, we process the number 9, adding it to the dictionary with a count of 1, so frequency becomes 5, 2, 7, 1, 9, 1. Finally, we encounter the number 10 and add it to the dictionary with a count of 1. At the end of this step, our frequency dictionary is fully populated as 5, 2, 7, 1, 9, 1, 10, 1. Now, we calculate the sum of unique elements. We initialize unique_sum to 0 and iterate through the frequency dictionary. The first number, 5, has a count of 2, so it is not unique, and we skip it. The next number, 7, has a count of 1, so we add it to unique_sum, resulting in a running total of 7. Then, we process the number 9, which also has a count of 1, so we add 9 to unique_sum, making it 16. Finally, the number 10 has a count of 1, so we add 10 to unique_sum, giving us a final value of 26. With all numbers processed, we find that the sum of unique elements is 26. This is the value we return as the output. By following this approach of building a frequency dictionary, identifying unique elements, and summing them up, we can solve the problem efficiently for any given input array. To analyze the time complexity of the given solution, we break it into two distinct phases, constructing the frequency dictionary and calculating the sum of unique elements. In the first phase, we iterate through the nums list once. For each element, we check if it is already present in the dictionary and either update its count or insert it as a new key. Dictionary operations like lookups and insertions have an average time complexity of O(1) due to the hash table implementation. Since we perform these operations for all n elements in the list, the time complexity for this phase is O(n) on average. In the second phase, we calculate the sum of unique elements by iterating over the frequency.items. Since there are at most n unique elements, this requires a constant time check for each key-value pair and potentially adding the key to the sum. These operations also contribute O(1) per element, leading to O(n) time for this phase. Combining the two, the total time complexity of the solution in the average case is O(n). Adding up the complexities of the two phases, we have O(n) plus O(n), which simplifies to O(n) overall. In the worst-case scenario, dictionary operations like lookups or insertions can degrade to O(n) per operation due to hash collisions. If this happens, constructing the frequency dictionary could take O(n)² time. However, Python dictionaries are highly optimized, and this is a rare occurrence. In the best and average cases, where hash collisions are minimal, dictionary operations remain O(1), and the overall time complexity stays O(n). Next, let's look at the space complexity. The primary contributor to space usage is the frequency dictionary. This dictionary stores a key-value pair for each unique element in the input list. In the worst case, where all elements are unique, the dictionary contains n entries. This results in a space complexity of O(n). In addition to the frequency dictionary, the solution uses a few auxiliary variables, such as unique_sum, number, and count. These variables require constant space, or O(1). Therefore, they do not contribute significantly to the overall space complexity. When we combine the space needed for the frequency dictionary and the auxiliary variables, the total space complexity remains O(n). In the worst case, where all elements in the input are unique, the dictionary size grows linearly with the input size, resulting in O(n) space usage. Even in the best case, where all elements in the list are identical, the algorithm still requires O(n) space to process the input list. This is because the dictionary must account for all elements during the iteration, regardless of whether they are unique or not. To better understand the efficiency of the optimized approach, we can compare it to a brute force solution. A naive method might involve using nested loops to manually count the occurrences of each element in the list. This would lead to a time complexity of O(n)². As for each element, we would iterate through the entire list again. While this approach has a space complexity of O(1), since it doesn't use additional data structures, the trade-off in terms of time is significant. In contrast, the optimized solution reduces the time complexity to O(n) by counting occurrences in just one pass using a dictionary. Although this increases the space complexity to O(n) due to the dictionary, the improvement in time complexity makes it a far more efficient solution overall. The time complexity of the solution can also be confirmed mathematically. For dictionary operations like lookups, insertions, and updates, the average case is O(1). This assumes the hash function distributes keys uniformly and collisions are rare, which is generally true for Python dictionaries. Additionally, the algorithm includes two linear scans, one over the input list and another over the dictionary's key-value pairs. Both of these are O(n) operations. Adding these together, the total time complexity is O(n). The space complexity is O(n) as well, primarily due to the storage requirements of the frequency dictionary. This analysis confirms that the solution is both time and space efficient for the problem at hand. When solving this problem, there are several common mistakes to watch out for. First, overlooking edge cases can be a significant issue. For example, you might forget to test arrays with only one element, arrays where all elements are the same, or arrays that contain duplicates except for one unique value. These scenarios are often used in interviews to evaluate how robust your solution is, so missing them can lead to failure. Another frequent mistake is using nested loops to solve the problem, resulting in an O(n)² solution. While this might work for small inputs, it becomes inefficient and can lead to timeouts for larger arrays, especially when n exceeds 10,000. Additionally, errors with hash map operations are common, such as forgetting to initialize keys or mismanaging element counts. These can cause runtime errors or produce incorrect results. Finally, misinterpreting the problem requirements is another pitfall. For instance, confusing exactly once with appears an odd number of times can lead to implementing the wrong logic and failing key test cases. Another mistake to avoid is failing to optimize space usage. Using extra data structures unnecessarily can be problematic, especially when a constant space solution is achievable. In interviews, ignoring space constraints might disqualify your solution, even if the time complexity is optimal. Shifting to some interview-specific insights, it helps to recognize common patterns in problems like this. For instance, single occurrence problems often utilize XOR operations or hash maps. If the input can be sorted, consider whether sorting simplifies the problem by grouping duplicates together. In terms of approach, interviewers typically prefer O(n) solutions when constraints are large, so aim for linear time complexity whenever possible. Additionally, minimizing space complexity is crucial if you can solve the problem in place. That's often the preferred method. Lastly, remember to communicate your thought process clearly to the interviewer. Start with a brute force explanation, then iterate toward an optimized solution. Always clarify edge cases and problem constraints before you begin coding to ensure your solution aligns with the requirements. To deepen your understanding, it's useful to look at related problems that share similar concepts. For example, in LeetCode 136, single number, you need to find the one element that appears only once when all others appear twice. LeetCode 137, single number 2, is a variation where each element appears 3 times except for one. Another related problem is LeetCode 260, single number 3, where you're tasked with finding 2 numbers that appear only once, while all other elements appear twice. Lastly, LeetCode 268, missing number, involves finding a missing number in a sequence and can be solved using a similar XOR pattern. Exploring these problems can strengthen your grasp of the techniques and patterns involved in solving unique element problems. There are also several alternative approaches to solving this problem, each with its own trade-offs. The hash map approach is a straightforward method where you count the occurrences of each element using a hash map. While this is easy to implement, it requires O(n) space, which might not be ideal if space constraints are tight. Another option is the sorting approach. By sorting the array, you can identify the unique element by comparing neighbors. This reduces space complexity to O(1), but it increases time complexity to O(n) log n due to the sorting step. Finally, there's the bitwise XOR approach, which is both time and space optimal at O(n) and O(1), respectively. This method works by leveraging the property of XOR. Duplicates cancel each other out, leaving only the unique element. While this approach is highly efficient, it can feel less intuitive, especially for beginners. Each of these methods has its advantages, so the best choice depends on the problem's constraints and your familiarity with the techniques. Great job on completing problem number 1748. To recap, we tackled the problem by identifying unique elements and summing them up. This problem highlighted key concepts like using hash maps for tracking occurrences and optimizing for efficiency. Keep up the great work, and remember to practice regularly. Thanks for joining, and see you in the next problem walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!